to y'all today about. Hello, my name is Sydney Calendar, and I'm here to talk to you about conservation of mechanical energy. So, as you can see, my mass, potential energy is mass times gravity times height. Kinetic energy is half times mass times velocity squared.
Cars increases mass, and therefore the total energy in your system. Subtracting cars will decrease the total energy in your system.
So let's start out with a really great mass, so you can understand this concept like a lot. So the highest I can have my mass is 8 cars, 800 kilograms. Each car, 100 kilograms, okay? 4, yep.
Notes to construct your track. Add hills and lakes.
As you can see, I've already
to introduce energy into your system.
Okay, as you can see, okay, really? So as you can see, I've already created a track for us, and I guaranteed that it works. So you're going to go up, down, a loop, and up again. The highest we're going to get there is 55.6, and the lowest is 5.3, and you're going to see why I have such a high and low thing. So the Swift Red Squid is going to go all the way up. Too much potential energy, and the energy will not make it. But as you can see, my kinetic energy goes all the way down. Kinetic energy goes up as we get lower to the ground. Potential energy goes down, up, as we get higher from the ground, which is kind of weird. And then we're going to crash, and I'm sorry that we did crash, but it was the only way I could actually effectively show you how potential and kinetic energy go against each other. Right, so here's the graph. The lowest point, and the highest point right here was 463.5 kJ and a 19.6 kJ for my kinetic and potential energy. You see, the higher we went up, the more potential energy we had. The lower we went down, and the higher we went up, the less kinetic energy we had. You see how they balance off each other with that? Now, okay, it has to equal, and so we can make sure that I get my math right. It has to equal 436.5 kJ. Kinetic energy has to equal 19.6 kJ. They do not have to equal that exact number, but you'll see why. Okay, so the mechanical energy is the addition of both those. And to make sure, look, I'm going to use my handy dandy calculator and my phone to make sure I get the right number for you folks. Okay, so 436.5 plus 19.6, which will equal 456.1 kJ for mechanical energy. Right. So the lower we go, and there's two low points, as you see. There's 353.4 kJ, and we have 320. So as you can see, this is the lowest point. So yeah, okay. So, as I said, lower we go, higher the kinetic energy goes. Lower we go, lower the potential energy goes. So you can see that 352.1 and 45.0 does not equal 456.1, but it will, because there's also dissipated energy. You gotta remember that energy does go away sometimes because we're using it. So 352.1 plus 45.0 will equal 397, plus the dissipated energy of 59.1 will equal 456.2, which is our mechanical energy, which is what we're conservation of mechanical energy. Right. So this is real world applications. You got to remember this. I'm going to show you one which is a perfect, as we wanted to say, perfect example of what conservation of mechanical energy looks like. So our mass is 800 kilograms. Our speed is 30 meters per second, and our height is 5.7 right here. And right here, our speed is 7 meters per second. Our height, 55.2, and mass, 800. The only time speed affects kinetic speed only affects kinetic energy because we call it velocity, and height affects potential energy. So as you see, and I'm going to give you a perfect definition. Potential energy, and I have it up here. Potential energy is the energy stored in the object as a result of its vertical position or height. So, but kinetic energy is the energy released from an object due to its speed and our velocity and mass. Right. So, let's go to an actual example, or the one we like to call the perfect example of potential and kinetic energy. Here it is. So, as you see, kinetic energy, this is why it's perfect. Because kinetic energy can never be zero for our potential energy to be 50,000 joules. So that will just release. So it just goes. Like, it's okay. It's not, as you saw, if I will show, I could potentially show you in the next video that if kinetic energy was to be zero, potential energy would just not move. It's just too much object stored. It wouldn't move anywhere. It's gone. But perfect example. So, and my height's 100 meters, so that's how it's 50,000. So, as it goes down, kinetic energy is 20,000. Potential energy is 30,000. Right? Always equaling perfect 50,000. And right here, 30 meters is 35,000, 15,000. Because, you know, as we got closer to the ground, potential energy decreased. Kinetic energy increased. And then right here, where she jumps from this little thing to here, is 60 meters. And my potential energy is higher than my kinetic energy because we have gotten higher than that part. But say we touch the ground fully, my potential energy is 0. My potential energy is 0, and my kinetic energy is 50,000. Right. So now you've seen a perfect example, and you can compare it to our roller coaster real world application. And now you judge which one's right. Thank you for coming to this tutorial, and I hope you have a good day.